Well, we'd like to talk about an important topic here called vector addition. This will be useful throughout the year. Here are some details that we may not need to keep track of and follow the whole year, because I'm more concerned that you get the overriding concept than that you follow these details of format, but we'll just list them here for you anyway. A vector quantity is a physical quantity that has direction as well as magnitude, and magnitude is something like size or amount. Vectors are drawn as bold-faced arrows. We're just going to draw them as arrows, and they indicate the direction of the physical quantity, and the length represents the magnitude or the size of that quantity. And this is a technicality of notation that we probably won't observe, but it may be important later in a college course. The vector itself is represented by a letter in boldface, and its magnitude, which is just its amount or size, would be represented by that same letter but in italic font. All right, you're familiar with vectors. If you've ever watched weathercasts, or if you've watched storm reporting, especially maybe with hurricanes. Here's an example of a map given concerning Hurricane Katrina, and you can see all these little vectors. You can see the long red vectors. You can see the small yellowish or orangish vectors out toward the edge, and all these vector quantities are different, or the vast majority of them are different from any of the other vectors on the page. How are they different? Well, there's the matter of length. Now, I guess whoever is making this map color-coded them too, but color coding wouldn't be necessary. The length tells you the amount, and of course their arrows pointing in a particular direction. So you can see the direction of the wind and the speed of the wind. The direction by the way the arrow is pointing, and the speed by how long the arrow is. And so this is a vector representation of wind velocity, technically, because velocity is the vector quantity that has both direction and magnitude. Okay, we've got to ask ourselves, do units matter? Here we have 4 equal length vectors, and they all have the number 88 associated with them, but they also have these extra units such as meters, meters per second squared, and newtons. I want you to realize that different vector quantities are represented with their different units. It's important to see the units. 88 meters, this is a displacement. It just tells us how that we're removed 88 meters from the origin. It doesn't tell us how fast we're going. It doesn't tell us if we're speeding up or slowing down. In contrast, this second vector represents a velocity. And if this was the only velocity throughout the whole problem, then that would be constant velocity. And there's the sound effect of constant velocity. We would know how fast we were going and in what direction. What these all have in common, by the way, is that they're all representing the same direction, which you might say was east or to the right, depending on what your perspective is. And we know its speed in this direction. We know speed is the magnitude, the 88 meters per second, and the direction is to the east. This next vector, the third one, represents an acceleration. The units meters per second squared indicate to us this is an acceleration. That means for every second that goes by, we're speeding up we're gaining speed by 88 meters per second. That's an incredible acceleration, by the way, almost 10 times the acceleration due to gravity. So that would be an incredible acceleration. It wouldn't sound exactly like this, probably, but you hear the sound effect of an acceleration, right, with speeding up. So what this vector represents is that to the east, we're speeding up faster by 88 meters per second for every second that goes by. And this last one is in newtons, a unit we may not cover for a few weeks, but that's the unit for force. And a force causes a mass to have an acceleration. We wouldn't know what the acceleration was based on this force unless we knew the mass of the object, and we would have to do some math to figure out what the acceleration would be. But what this does represent for us is an amount of force applied in the eastward direction, or to the right, 88 newtons. So these have totally different meanings because of the units. The only thing they have in common is that they're in the same direction. Now, vector quantities that have different units cannot be just added together or subtracted from each other, and this should agree with what you remember about the rules of algebra. Here I give you an example. We've got a sum to do here, and it shows 34x plus 65x squared plus 37y minus 14x plus 22y. If you add those up, you can't just combine all those terms. You can combine things that both have x's in them, so we'd have 30 minus 14 is 20x. You can combine things that both have a y, and that's 37 plus 22 to make 59y. But we can't do anything to combine the 65x squared with anything else, so it has to stay by itself. So when we combine vector quantities, we can only combine vector quantities that have the same kind of units. Here I want us to consider an example. This would be a certain kind of physics problem you might encounter. It says, consider an airplane traveling at an air speed of 45 meters per second in wind that is blowing at 54 meters per second. So to the plane's perspective, it's going through the air at 45 meters per second. But the wind is blowing at 54 meters per second. Let's say that this is our vector for the wind speed, and we haven't specified a direction yet. There's the vector for the wind speed, and here's the director. I'm sorry, that was for the airplane's airspeed, and this yellow vector is going to represent the wind speed, 54 meters per second, and again, haven't specified a direction. So we have to ask ourselves, does direction matter? Well, let's consider this. If the plane's airspeed is 45 meters per second and the wind is blowing in the exact same direction at 54 meters per second, then it should stand to reason the plane is passing through the air at 45 meters per second, but that very air is moving at 54 meters per second, and so we get an overall speed compared to the ground of 99 meters per second. How about if the plane's airspeed was 45 meters per second to the left or to the west instead of to the east, and the wind was also blowing to the left or to the west instead of to the east? Again, these would add up to a total of 99 meters per second, but to the left or to the west. And so I want you to notice here that we've put negative signs to indicate opposite directions. Okay, positive, negative tell us opposite directions. And so it's you might say, well, 99 is 99 meters per second, 99 meters per second. In either case, why do we have to put a negative on there? Well, whether you're going 99 meters per second forward or 99 meters per second backwards is a very different experience if you're in the vehicle, right? And it's going to take you to very different destinations. So direction matters, and we represent it with sign when we put the numbers into our, if they're along the same axis, and we're putting them into our math problem. Okay, here we go again. Does direction matter? Well, let's say that the wind speed is 54 meters per second to the east, but the airspeed of the plane is negative 45. It's 45 meters per second to the west. So what we have there is the plane is trying to fly against the wind. The wind is blowing to the east. The plane is flying to the west. And so how fast is that plane going after it all cancels out? It's actually going to the east. The plane's trying to fly to the west, but it's actually flying to the east at 9 meters per second because it's going against the wind. The wind speed is faster than the airspeed of the plane. We could have the other example. We had the wind blowing 54 meters per second to the west, the plane flying with an airspeed relative to the air 45 meters per second, and so we end up with the plane going to the west at 9 meters per second. Here's a little example, just a little fun video you might like to see, just showing birds trying to fly against wind that's too fast. Some of them you can see are even going backwards. Poor birds. All right, so direction does matter.